morning. Welcome to today's lecture on sustainable manufacturing, and we are going to study today basic statistical concepts that are required for conducting analysis in related to sustainable manufacturing. We have already seen the hierarchical structure of sustainable manufacturing, where we look at from the factory view to the production line view to the unit manufacturing processes and the need of analyzing them at that process. And we have also seen the usage of the importance of simulation and its usage as an important tool for doing analysis of sustainable manufacturing systems. Since many of you are not from the does not have the probability and statistic viewpoint or exposure to that course, today we will kind of cover the very basic concepts of it in a very simplified manner, and it might help you in understanding some of the concepts that are presented in this course. So, the major agenda of today's discussion would be the random variables and why it is necessary, and this is required to, we basically use this to study system state, especially in this case we are going to study the state of this sustainable manufacturing system. We need to study the independent and randomness for simulation analysis. We need to study the covariance stationary process, that the importance of it for what we call as the steady state analysis. And also the transient analysis. We study the law of large numbers for what we call as replications, and averaged estimates. This concept is important here. Then we look at the probability distributions and mean to model various manufacturing process. So, in this we model the process times or processing times as we call it, setup times, and we also talk about it as the downtimes. There are many aspects of this we can model as part of this, okay. And we also look into the test of independence as well as part of this, okay. So, for detailed information about this, I would recommend you two textbooks. One is Probability and Statistics, for engineers and scientists, the author is J.L. DeVore, and the second book is, we would call it is Applied Probability and Statistics for something engineers and scientists by John Miller et al. The multiple of this, it's typically known as Miller and Font textbook, okay. All right. So, with this, let's get into today's concepts, and let's see whether we can understand basic aspects of it. So, the first concept we are going to do today, the basic terminologies that you need to be familiarized with this course, which will be used repeatedly throughout this process, will be the concepts of experiment. The first one will be experiment, then we will talk about its sample space, and then we talk about its sample points. So, the experiment is typically, it's a process whose outcomes are not known with any certainty, and means in simplest way there is uncertainty associated with the outcome. So, a simple example of this is tossing a coin, tossing a fair coin. So, in a fair coin you have you make a toss, you can either get a head or a tail. So, if you make a toss now, you do not know whether it will be a head or a tail. It can be head, it can be tail. So, the outcome is not known with quite a large amount, is not known with certainty. You cannot really say it is going to be head. You can say it is head, it could be head or tail. So, experiment is any process like that. So, here this is an example of an experiment. The another example would be rolling a fair die. When you do this, again the thing is you could get any of the values from face values of 1, 2, 3, 4, 5 and 6 are the possible values that you can get out of this. You can get any of those faces. You are not sure which value you are going to get. Next concept that we need to go through is the sample space concept, the concept of sample space, which by definition is the collection of all possible outcomes of the experiment. So, as we said earlier, if the experiment is rolling a fair die, then all possible outcomes, okay, if you write it as a set, then the sample space is denoted by capital S or uppercase S. The set would be 1, 2, 3, 4, 5 and 6. This would be the when you are rolling a die. Similarly, if you are tossing a coin, the set would be head and tail. This is tossing a coin. So, sample space is the set, the collection of all possible outcomes of the experiment is when expressed as a set is what we call as a sample space. Then we talk about sample points. Okay. So, all the outcomes are the sample points in the sample space. So, you are rolling a fair die and you get the face value is 1. So, this is a sample point, this is another sample point. So, when you say S equal to 1, 2, 3, 4, 5 and 6 for rolling a fair die, then 1, 2, 3, 4, 5 and 6 are the sample points. So, I hope you guys understand that. You can also create an experiment where you can say that I am rolling a die and tossing a coin at the same time. So, then you can have a head or a tail and along with that any value that is possible. So, you can have if you write both of them at the same time, then the sample space would be you can have head and then 1 on the die, you can have head and 2 on the die, you can have head and 3 on the die, head and 4 on the die, head and 5 on the die, head and 6 on the die, then you have tail and 1 on the die, tail which is on the coin and 2 on the die, tail and 3 on the die, tail and 4 on the die, tail and 5 on the die, tail and 6 on the die. Okay. These are the possible options. So, you can see that as the experiment gets complicated. Okay. So, here what we did is we tossed a coin, tossed a fair coin and rolled a die. So, you can see there is a sample space, the size is increased. Similarly, as the experiments gets complicated, your sample space keeps on increasing. Okay. So, then we talk about the concept of random variable. We did kind of cover this in the yesterday's lecture, but more formally random variable we define as it is a function. Random variable is a function, that is the first important thing that you need to know. It is a function that assigns a real number to each point in the sample space. So, it is a function that assigns a real number to each point in the sample space is what a random variable is all about. So, if you are talking about the problem of tossing a coin, let us take this again, tossing a fair coin. The sample space is equal to head or tail. Okay. So, now what does random variable do? Random variable assigns a real number to each point in the sample space. So, if I say that I get a head, we say it as win. which is equal to 1 and tail equal to applies its a loose and that's equal to 0, then the random variable of getting a head can be described as probability of capital X. X is the tossing a coin equal to 1, which means the probability that when I toss a coin, fair coin, and get the head, and I say this 0.5. So, this is what this function that maps the random variable which maps the outcome to a real value, that is what we call as. So, in this case the random variable is X. So, this is the random variable. Okay. So, random variable allows you to map the outcomes of an experiment to a real value in the sample space, right. So, I can also say on the same line I can also say that probability of X equal to 0 equal to 0.5, which means if I toss a fair coin and I get a tail, and that probability is also 0.05. So, this is again this random variable is denotes the experiment of tossing a coin. Now, when you have, so similarly some people express this in different ways. So, if you talk about rolling a die, so if we talk about the rolling a die and I say let the random variable be y and I get a face value of 3. So, then this probability equal to 1 over 6. Okay. So, the values this random variable y can take are equal to 1, 2, 3, 4, 5 and 6. So, we typically represent this as probability of big Y equal to little y, or here you will write it as probability of big X, capital X equal to little x. Okay. So, this is the value, this is the random variable value, this is the value, this is the random variable. So, so you know that now random variable is a function that assigns a real number to each point in the sample space. Now, when you have the entire random variable and the associated probability along with it, when you describe that, then that becomes the probability density or probability mass function. There are multiple names people use it: probability density, probability distribution, probability mass function, many names for it. But at the end of the day, they are all pretty much the same. It is it represents the values the random variable can take along with its respective probabilities. So, if I had to write the probability density function of rolling a fair die, so I would say like this: x, so this is the value, this is the value that random variable can take, and that will be 1, 2, 3, 4, 5 and 6, and I will write as probability of big X equal to little x. So, this is the probability that the random variable take any of these values, and I write those probabilities as 1 over 6. This becomes the probability density or probability mass function, distribution function, whatever you want to call it. It typically known as the PDF. Okay. This tells you how the random what are the values the random variable can take and the associated probabilities with it. So, this is a case of a discrete. Okay. So, this is discrete. Why is it called discrete? Because the outcomes are separate, countably definite. There can also be a continuous process in which the value of the random variable can change continuously. A classic example of this would be a scenario where the random variable, here is your numerical value x, and here is the probability x equal to little x, and you can have the random variable take any value between a and b. So, here this kind of a system is called a what we call as a uniform distribution, but here the random variable could take any value in between this with equal probability. Okay. So that is again, so in this case the random variable is continuously distributed between A and B. So any value between A and B it can take. Now the cumulative density function or distribution function, which is typically known as the CDF. Okay. This is another aspect. You get CDF from the PDF. There again, they both can be discrete or continuous. So if you want to do probability of CDF for the rolling a fair die, when I say probability of x less than or equal to 4, what that means is, what is the probability that I get an outcomes of 1, 2, 3 and 4. That is what it means. So how do I get that? That is equal to probability of big X equal to 1 plus probability of big X equal to 2 plus probability of big X equal to 3 plus probability of big X equal to 4, which is equal to 1 over 6 plus 1 over 6 plus 1 over 6 plus 1 over 6 equal to 4 over 6. Okay. So this is the probability that I roll a fair die and I get any value less than or equal to 4. Okay. So that cumulated probability, this is the cumulated probability. Okay. So the cumulated probability of this happening, any of the phase less than or equal to 4 happening, so this is a discrete case. Okay. That is the CDF, cumulative density function. Okay. In the case of a continuous distribution, what you will be doing will be, so here in this case, in a continuous, the PDF can be typically represented as an integral. So there you will write it as integral a to b f of x dx. This f of x will be a function. So in this case, it will be like if you are going to go to a particular value, you say probability of x less than or equal to little x, you will be integral of minus infinity to x f of x dx. So integrate from negative all the way up to x. So here in this case, if you are looking at a discrete uniform distribution, again if you take a look into this and you say that this is a, this is b and somewhere here is x, so then this is the total area that you are talking about. What is the probability that the random variable can take any value between, this is x, okay, x to a, that is what you are looking at. So that is the cumulative probability function. I would request you to read it more. I am trying to give it in a much simpler version so that everybody can have a fair idea, but please read the textbook for accurate information and as well as getting the proper terminologies right, and as well as looking at the solved solutions or examples. So then we get to the concept of mean and variance. Mean and variance are two important aspects which actually used to measure certain behavior of the data. Okay. So these are measures on the behavior of the data. Okay. The most important thing is the mean, typically what we call as it, or it's an expected value of a random variable. So when you say that, when you talk about a probability scenario where you are rolling a die and say probability of getting a little x, you said, and this is your PDF, and you have seen that the values of x can vary from 1, 2, 3, 4, 5 and 6, and this probabilities can be 1 over 6, 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 1 over 6. Then the mean or the expected value of the random variable is all about in the long term what you will get to see. So this is also what you call as, if you repeat the experiment infinitely, it's not infinite, it means like long time. Okay. If you are doing this for a long time, what will the value converge to? Okay. So, you roll a die, get a value, note it down. You roll another, take a value, note it down. You keep on repeating this, and you take those values and you average them. What would that value be? Okay, that is called as the expected value. So, expected value can be always found out easily. The typical formula of expected value, it is notated by E of x. Sometimes it is also known as mu of x. Okay. This is a notation for mean or expected value. It is given by x times p of x, or this p of x is equal to probability of x equal to little x. Multiply by those probabilities, you will get the value. So, in this case it will be equal to 1 times 1 over 6 plus 2 times 1 over 6 plus 3 times 1 over 6 plus 4 times 1 over 6 plus 5 times 1 over 6 plus 6 times 1 over 6. And if you sum all of this, you would probably get a value close to 3.5, I believe. Okay. So, that means in the long term you keep on rolling a die, take the values, note them down on a piece of paper, sum them up, divide by the number of observations you have. When I am talking about, let us say, roll this die and do it up to maybe let us say 1000 times or something like that, you will see the value slowly converging to 3.5. That is the long time average or expected behavior of the system. So, or that is what the expected behavior of the random variable. So, that is what the concept of expectation is, and the same applies for continuous distribution as well. So, what does the mean says, or what does the mean provides information about? It provides one information which is called as a central tendency, or what is the, so central tendency is in a way what is that value which is the centroid of the data, or what is the central point of the data, which shows the central tendency of the data, or in the long time that is what the data values should be converging to. Okay. So, this also kind of says converging. Okay. Where will this value converge to? Okay. So, many a times the mean, we all know the statistical mean, it is told as x bar, okay, which we always say is as sigma x sub I divided by n. So, if we have values of x is equal to 7, 3, 10, then x bar is equal to 7 plus 3 plus 10 divided by n. N is number of observations, which is 3, that is 20 by 3. Okay. So, that will be the x bar, or which is the mean, which is the sample mean in this case. Okay. So, there is a difference between sample mean and population mean, which you can read from the example, but here we are talking about pretty much this expected value as the case. The other hand, you measure the central tendency, and the next thing you measure is the dispersion or deviation. Okay. Two ways you can measure it. One is by using the concept called variance. Okay. The variance of a random variable measures its dispersion. So, what it really measures is, it measures the deviation from the expected value. Okay. Yeah. So, in a way what you are trying to do is, if you have the mu and minus x is what you are trying to measure. So, if you know what is the expected value and there is x, that is the measure from the individual. So, then variance typically you square this, because you know, sorry, actually not that case, in the case of sample variance. So, the mu minus x, in a way what you are trying to say is how far is, if you look at a set of data like this, and let us say this is the sample mean, then these deviations are what you are looking at. Okay. Something like this. You can visually think about that as that way. So, important thing is variance is always greater than or equal to 0. It is never a negative value, because you end up squaring it, as I said earlier. Okay. If you just sum the deviations, then it can all sum to 0. Okay. That is one of the reasons we square, because there will be positive and negative deviations. When you square it, actually it becomes non-zero positive values, and then the lowest possible value you can get is 0. Whereas, the problem with the variance is the unit of variance is not as same as data. So, let us say if you assume these values to be, the unit will be degrees Celsius, then the variance of this will be, the variance will be given by, it can be calculated typically by like 20 by 3, that will be about approximately 6.8, something like that. 6.8, it will be 6.8 minus 7 square plus 6.8 minus 3 square plus 6.8 minus 10 whole square minus n minus 1. Okay. That will give you the variance, which is n minus 1 will be 3 minus 1. Okay. So, in this case, if the unit of this variance will be degrees Celsius square, because you are squaring the whole thing. This cannot be compared with the data value. So, hence to find a deviation which is in the same unit as that of a data value, we do what we call a standard deviation. So, standard deviation typically denoted by sigma. By the way, variance is typically denoted by either variance of x or sigma x. When it comes to sample, we basically say S square. Okay. So, that is a notation that is used, which basically says it is a variance anyway. Standard deviation on the other hand is, sorry, it is not sigma square. Standard deviation is sigma of x or S, this is a sample standard deviation, this is the population. Okay. So, this is given by square root of variance, that is what a standard deviation is. So, that you get the unit, has a unit same as that of the data, you get the unit back of the data. Right. So, moving on, I request you guys to go ahead and read these whole concepts of variance, expectations, expected value, mu, population mean, sample standard deviation, sample variance from the textbooks. This is just an overview of what the multiple chapters of the textbook covers, but hopefully it gives you an idea and motivation to read the whole thing. Now, we are going to study the concept of independence. So, the independence is a tricky concept because independence concept is important to conduct simulation analysis. This you guys need to remember, why you need to learn the concept of independence. So, we can say two events are independent, okay, if the occurrence of one event does not affect the probability of occurrence of the other. So, you have two events that are happening, and so first thing is two events are happening and one event happening is not decided by the happening of other or the occurrence of other. So, when you have such two events, those events are said to be, okay, they are independent events. Okay. Mathematically, it is given that, okay, the probability of A given B. Okay. So, that probability of A said that that B has occurred is basically this you can think about in the case of Bayes theorem. Okay. All right. So, the independent events must be able to occur at the same time, that is the most important aspect that you need to say. So, if you have a manufacturing system in which there is a milling that is going on and drilling that is going on, okay, they are connected with each other. Let us say a part is coming here, one part is here. This drilling of this part can only happen for this part, drilling can only happen after milling. Why? Because of precedence. For this particular part. But if you have another part, two different part, this is part 2, this is part 1. For part 2, drilling can happen if milling is happening for part 1, okay, assuming that it is over. So, what I am trying to say is that but if you had the factory like this, we draw it here, milling and drilling, and parts come and go to a milling, parts come and go to drilling, then you can say that the occurrence of milling does not influence the occurrence of drilling. So, then you can think about it as an independent event, where in this case you cannot really think about it as an independent event. Okay. Then there is another event which is called about disjoint events. So, please read that in the textbook. Disjoint events cannot be independent. Okay. Disjoint events, the reason they cannot be independent is because they cannot happen at the same time. So, an example of this is when you toss a coin, you can get a head or you can get a tail. You cannot get a head and tail at the same time. Okay. So, they are disjoint. That means there is so if you think about a disjoint events, and if you think about it, the probability of event A and probability of event B, there is no connection between them. They are not, the probability of intersection is actually equal to 0. So, this is A and this is B. Okay. So, disjoint event means they cannot happen at the same time. There is no probability of them happening at the same time. Not disjoint events may or may not be independent. Remember this. This is important. The disjoint events, okay, they cannot be independent. If the event, so that does not mean that not disjoint events. If the event is not disjoint, that does not mean they are independent. They are may or may not be. Not disjoint events may or may not be independent. That is the other important aspect. Anyway, the concept of independence is important for simulation analysis is purely because we analyze systems like this, we analyze systems like these. So, for such systems we would really like to study the concept of independence, okay, or at least understand the concept of independence, so that when output data of simulation is analyzed, appropriateness can be created. Okay. So, continuing on, here is an illustrative example for what we presented earlier. Let us think about an experiment. So, here is an experiment for you. So, this is an experiment. Draw a card from a deck and bet on whether the color is red. Okay. So, the experiment is this: you draw a card from the deck and you say whether it is red or black. Before placing, so if you think about this whole experiment, before placing the bet, it is told that the card is spade. Okay. So, that means you know what the colors are. Okay. You have a if you draw a card, you have what you call as, one is called as the clubs, which kind of looks like this. Excuse my drawing capabilities. Another one is the hearts. Okay. Another one is called as the diamond, and third one is the spade, which kind of looks somewhat like this. Yeah, my drawings are bad. So, these two are the red guys and these are the black guys, right. So, before placing the bet, you are told that the card is spade. Spade means, okay, red and spade are disjoint events, but so that means it cannot, if it is a spade, it can only be in black, it cannot be in red. So, that means red and spade, they cannot happen at the same time, they are disjoint events. So, that means red color card and spade, these two cannot happen simultaneously. Okay. So, the information, you know that is disjoint, that means they cannot happen simultaneously, and you have to bet whether the card is red or not. So, if somebody says you the card is spade, then you should not bet on red color, because it is not going to be red, it is going to be black. But that, hence that information influences the bet. Okay. This information that spade is black in color always influences the bet. Okay. But if I tell you that instead of telling it's a spade, if I tell you that the card is ace, okay, ace is represented in a card as like it will something like this, A, and if we have something like this, that means it's an ace of a diamond. So, this is ace of diamonds. Okay. So, if I say that the card is ace, okay, then the red is not disjoint, because you have an ace for diamond, you have an ace for heart. Okay, these two are red. Then you have an ace for a clubs, which will be something like this. Okay, and you have an ace for a spade, which will look something like this. Okay. So, these two are black, these are red. So, 2 out of the aces are red, 2 out of the aces are black. So, now you have that ace, it can be black, it can be red. Okay. So, that means they are not disjoint, or in a way red and ace can happen at the same time. So, they are not disjoint, but they are independent. How are they independent? Because red is independent, because the probability of red is 1 over 2, because there are 52 cards in a deck. So, total cards in a deck equal to 52. Okay. 13 cards in 4 suits. Okay. These are the suits. Okay. So, that gives you the 52. Okay. Then so that means you have 13 plus 13. So, the black is 13 plus 13, red is 13 plus 13. So, this is the clubs and spades, club and spades, this is the heart and diamonds. Okay. So, you have 26 cards that belong to the red color suit, and of the total 52. So, the probability is given by probability is equal to outcomes, number of outcomes favorable by total outcomes. So, in that, if you follow that formula, the 26 favorable outcomes for getting the card, the red card, and that total of 52 cards. So, you get the probability of 1 over 2. Probability of red given ace, there are 4 aces. So, in this case the total number is 4, this is the total outcome, which is 4, and there are 2 out of the 4 are red aces. So, it is 2 out of 4, which is equal to 1 over 2. So, the occurrence of ace has no influence on the occurrence of red, because it can be any one of those, but they are independent events and they are not disjoint. Okay. So, if an event is disjoint, so think about this way, disjoint events are not independent, Why? Because they cannot occur at the same time. Okay. Independence do require the occurrence of the same time, and the occurrence of one should not influence the occurrence of the other. So, the occurrence of the A's has no influence on the occurrence of red, because A's can be in red or a black. Okay. So, the red and A's, has the occurrence of an Ace does not influence the occurrence of the red card. Hence, you can say that occurrence of an Ace and occurrence of a red card are two independent events. But occurrence of a spade and occurrence of a red are not independent, because they are disjoint events, because if it is a spade, it cannot ever be red. I hope that kind of makes the concept clear to you guys. So, here is another example, a little bit more realistic example. Let us forget about the cards and let us worry about this. Color blindness. Color blindness is that you are not able to identify the color. So, not being able to identify the color. This is the color blindness concept. Okay. So, color blindness occur more often in men than in women. Okay. Actually, it is not woman, women, WOMEN, the plural. Okay. I apologize. So, men are more, so in a way the best way to say this is men are more prone to color blindness than women. All right. That means, okay, a woman can also be color blind. It says that, okay, men are more prone, does not mean that woman can never be color blind. She can also be color blind, and if that is the case, then the events are not disjoint. Why? Because disjoint, as remember earlier, cannot happen at same time, but woman can also be color blind, they are not disjoint. Given that the probability of a woman being color blind is much lower, sex and color blindness are not independent either, because you already said that if you say sex equal to, let us say you think about this way, male and female or men and women, and if you put the probability of this x, then let us say the male probability is, if you put the female probability as let us say 0.4 or something like that, the probability associated with men will be obviously more than 0.4, maybe 0.6 or 0.7 or something like that, some value. Okay. The idea is that probability of color blindness in men is greater than probability of color blindness in women. So, given this information, you can say that if you know the sex, okay, then the occurrence of color blindness, the sex and color blindness are not independent either, because sex do influence, sex influences the occurrence of color blindness. Okay. So, this is another illustrative example of how independence is important. So, if sometimes certain things, so in a manufacturing system, if something has happened earlier, so the occurrence of something, or if the occurrence of something do influence the occurrence of another, then they are not independent events. So, then when you are doing analysis, they should not be analyzed as independent events. That is the most important aspect that you need to think about. So, we talked about independence. So, if it is not independent, then obviously they should be dependent. So, if you are dependent, how do you measure the dependence? So, this slide talks about how to measure dependence. In simulation, lot of the events are dependent. Simulation, lot of events are dependent. So, you need to have a mechanism to measure the dependence. Okay. And what is the measure of dependence in this case? Typically, the measure is given by stuff called covariance. So, covariance measures the dependence, the linear dependence of two random variables. If you have two random variables x and y, okay, so random variable 1 equal to x, uppercase x, random variable 2 equal to y, uppercase y, then covariance of x and y, or in a way the linear dependence of x and y is given by the expected value of x and y, okay, expected value of x and y occurring together minus expected value of x times expected value of y minus the expected value of these x and y separately. Okay. So, that means if covariance of x y equal to 0, then the random variable is uncorrelated. Okay. That means there is no correlation associated with that. Okay. If x and y are independent, then the covariance is also 0. That is also true. So, if covariance x y equal to 0, then you can say that they are uncorrelated, or other way they can also be independent. They are independent actually. Okay. Random variables can be positively or negatively correlated. So, what does that means is, if you have a variable x, okay, if you think about a scenario where you have x and y like this, and you draw the graph and you get something like this, that means as x increases, y also increases, and you do the covariance and find the correlation behind that, or the correlation coefficient, you get a value and it is, let us say 0.95 or something. The correlation value usually, okay, is measured by correlation coefficient. I am not spending time on how to do correlation coefficient. I request you to study this. So, there are many of them, is Spearman's rho, Carl Pearson's coefficient of correlation, etc. They are all there. Okay. So, the correlation coefficient typically in an example is Carl Pearson's coefficient of correlation. It varies between -1 to +1. Okay. So, -1 is, it is negatively correlated. This is positively correlated. So, what I am saying here is, if you have a 0.95 value, that means it is close to 0.1, is close to +1. So, that means the x increases, the value of y is also increasing, that means they are positively correlated. If you look at something like this, is an x and a y, and you have a data value doing this, okay, that means as x increases, y decreases. So, you might get a value of -0.8, that means x and y are negatively correlated. Okay. That means as x increases, y decreases, y shows a negative linear dependence on x. Okay. That is measured by this in this particular case. Also, for engineers, this correlation coefficient is distributed. If you think about this, here is your -1, here is your +1, and here is your 0. So, typically from, if you take 0.8 here and let us say -0.8 here, these are basically said as strongly correlated area. This is a strong correlation, which means this is a strong positive correlation, this is a positive correlation. Okay. Here is a negative correlation, but this is also strong, okay, strong correlation. So, this means a strong positive correlation as x increases, y increases. This means a strong negative correlation as x increases, y decreases. Now, let us take another example of another point of 0.5 and -0.5. So, this area is what we call as moderate. Okay. this is moderately correlated, this is moderately positive, this is moderately negative correlation. Okay. So, then another value that is possible is 0.3 and minus 0.3. Typically, we call this as weak correlations, okay, weak positive and weak negative correlations, and this area typically is taken as no correlation. So, you can think about the correlation coefficient. If you measure the correlation coefficient, you can identify whether strong positively correlated or strong negatively correlated, that kind of an aspect. So, it gives you the behavior of one random variable, or it measures the linear dependence of two random variables, how one random variable is linearly dependent on another. Okay. So, if covariance is equal to 0, if you measure covariance and covariance turns out to be 0, you can say that the random variables are not correlated. And if x and y are independent events, no matter whatever it is, if x and y are independent, then covariance of x and y should be equal to 0. Okay. So, for independent events, you will get the covariance of x and y, where the variance of x along with the variance of y, comparing the covariance together variance of that, you should be able to get a 0 value for that. And I said about the positive and negatively correlated, and correlation is measured by multiple correlation coefficients. So, I expected you to study at least two. One is the Carl Pearson's coefficient of correlation, that is one. The other one is Spearman's coefficient. People call this as Spearman's rho and those kind of things, but these two are quite important for us for this class. Okay. And because these coefficients of correlations are usually measured when you are doing analysis, simulation, output data. Okay. When you are doing that, when you are analyzing the simulation data, which is a large set of data, you always need to see whether the data is dependent, independent, there is correlation between the data, is it positively correlated, is it negatively correlated, stuff like that. An example of simple example, way down the road you will actually read, we are using a specific type of cutting fluid. Okay. So, use of cutting fluid on surface finish. Is this correlated, not correlated? That is one thing that is typically studied as part of the sustainable manufacturing analysis. So, I think what we will do today is we will kind of stop here and take the rest of the topic as part of, and second few more slides are left out. We will actually take this as a continuation in the next lecture, and with that we will complete the basic concepts or introductions of statistical concept to it. But please take your time to read and understand these textbooks and cover up the basics, so that you can understand the futuristic analysis of how to make a manufacturing system sustainable. Thank you for your patience here.